Hi, my name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln, and welcome to this video on galaxies, elliptical galaxies, and the fact that some of those elliptical galaxies probably aren't genuine elliptical galaxies. Now, if this is the first time you've come across one of my videos, I'm going to recap what galaxies are and the main types at the beginning, and I'm going to do that for most of my videos just in case you're coming across this for the first time. But if you're already familiar with those, then skip towards the middle part to the end part where we actually look at the lenticulars and why they actually might be kind of hiding there in plain sight as elliptical galaxies when they really aren't. So, for those of you who aren't aware, galaxies are these vast collections of stars, gas, dust, and also dark matter. In fact, we have a lot of dark matter that we can't actually see, but we can see their gravitational interaction, and they're bound together. And this is a kind of disk-like galaxy, which means it's rotating like a disk. There are other sorts of galaxies, and these are enormous structures. So you could have billions and trillions of stars in there, and depending on the sort of galaxy that it is, it will have various amounts of gas and dust in there and other sorts and different components. That's what makes the different sorts different, I suppose. So they come in a variety of different sizes and shapes. We've got disc-like ones, we've got jellyfish ones, which are kind of disc-like, but they have tentacles. They're quite unusual and quite interesting nonetheless. We also have elliptical galaxies, which are smooth and featureless. Spiral galaxies there's lots and lots of different sorts and shapes, sizes. It's endless, really, and we could do lots of videos, which I have done actually. So lots of different sizes and shapes. If we go to the Hubble classification system for galaxies, it looks a bit like a tuning fork, and there are different versions of this. They all pretty much follow the same sort of idea though. You have these two branches on the right hand side for spiral galaxies. The top branch is your normal spirals. That means they have a bright central bulge, which is spherical. The bottom one is barred spiral, so they have a bar in the center. That's actually like our Milky Way. Now, quite often you'll see a third one in the middle, which is intermediate. These are not quite a strong bar in the center, but they're also not spherical, so they kind of sit somewhere in between. But those spiral galaxies sit on the right-hand side of this diagram, and as they evolve and get older, they will go from the right to the left. So their spiral arms get more tightly wound, they lose their gas because it gets turned into stars, the stars get older, and stuff like that, basically. So they go from right to left. Now, generally, and these are fairly general rules, and this could actually be related to kind of disk-like galaxies. So we call them spiral galaxies because they have spiral arms. However, there are a few different versions that don't really have strong spiral arms. Like you can have ones that are more patchy, and they don't have complete spiral arms. But anyway, generalization. These have significant amounts of gas in. As they age, they obviously lose their gas. It gets turned into stars. But because you're forming new stars, they do have an abundance of younger blue stars. So overall, the galaxy might appear bluer than an older one. They have disk-like dynamics, which means they kind of rotate in a common plane like a disk, like all of the stars and the material are going around in a common direction in the disk at least. So they have these disk-like dynamics. Now onto the ellipticals, which is what we're interested in for this particular video. They sit on the left-hand side, and they are classified purely by shape most of the time. So they'll go from E0 to E7. E0 being perfectly spherical, and E7 being like cigar shape. So we basically identify those. They're featureless, they don't have spiral arms, and we would classify them purely by how elliptical they look, hence the name elliptical galaxies. Now, again, general rules here, but this is not necessarily true. So they don't have any star formation. That's not technically true. They have very low rates of star formation. They have more randomized motions of stars. So instead of having a disk-like dynamics, like a common rotation or a net rotation, the movement of the stars in the galaxy is more random. Now, they do have a net rotation, but the random motions are normally more significant. Like a higher magnitude than the actual rotation. So the random motions dominate essentially. Now the reason why they don't really have any star formation or have very weak star formation is because they have little to no gas. So there's nothing in there to collapse down to form new stars. So that's why you have no star formation. And then your populations of stars there are very old. So you have this old red stars there. So the overall galaxy would appear redder than an equivalent size spiral galaxy, because a spiral galaxy's got those younger blue stars. Ellipticals have much older red stars in there instead. Now, generally, again, this is not 100% true, but as a general kind of idea, your spirals, they merge into one another, so they will collide, and then you end up with your elliptical galaxies. So what that can do is it messes up the disk-like dynamics, disrupts them. The gas gets depleted because as they collide, it gets collapsed. You get a sudden burst in star formation, and then you end up with an elliptical galaxy. Now, you can get elliptical galaxies from a very large spiral without any collisions, but that's a whole other topic. But most of the time, we suspect that the spirals are colliding into each other to get ellipticals. We know that's at least the case for some of them because we can actually see them colliding. So on this diagram here, you're going from right to left, and they will essentially collide, and then you end up onto your elliptical pathway there. Now, interestingly, we have this group in between the two. So we have lenticular galaxies. Now, they share features, so physical properties and features of both spirals and ellipticals, and they sit in this kind of transition point between the two. So if a spiral galaxy was going to evolve into an elliptical galaxy over time without any kind of mergers, it would likely become lenticular. So what are lenticulars and what distinguishes them from other types? Well, they're disc-like, but there's no spiral arms. So they kind of, there's a picture here. You can see there's no solid, clear spiral arms there. They're just disc-like. So they do have disc-like dynamics. They're rotating like a disc, unlike an elliptical. Don't have the spiral arms. They're a bit more featureless. They've got gas. Sorry, they don't have gas, but they do have dust. So because they've got very low amounts of gas in them, you don't really have recent star formation. So star formation rates are very low, and you've got a population of old red stars. So straight away, you've got, let's say we've got no gas, old red stars, no star formation. That matches elliptical galaxies. So if we look at that, an elliptical, they share properties there. The big difference from an elliptical to a lenticular is going to be the disc-like dynamics. They're rotating like a disc, whereas the ellipticals are not. So these could basically be, as we mentioned, that they could be spirals that have just lost their arms, and then they've used up all of their gas. And over time, the spiral arms, you get a reconfiguration of the angular momentum, because the spiral arms don't rotate at the same velocity as the stars in the galaxy. So you can transport angular momentum, things like that, and the spiral arms can dissipate. Over time, that gas gets used up into creating stars. So the gas is depleted, and that you could then basically end up with a lenticular, and it would be a kind of a fainter version of an equivalent spiral because they get dimmer as the stars are aging, and you've got less bright young stars there. So let's go back to the ellipticals. Now it might be, well, it's not that might be, but it's almost kind of proven now that the far right half of the ellipticals on the diagram here are not ellipticals. So from E4 to E7, those ones that get quite elliptical, these are not elliptical galaxies. So initially, it was thought that they're all the same object, basically, but some are essentially more flattened than others. They're more elongated, and that's why they were then labelled with their shape. So from E0 to E7, purely on shape, because again, if you look at them, okay, they look quite red. They've got old stars in there. There's no gas in them, things like that. So there's no reason to believe that they were not the same sorts of object. So they both have the same stellar populations, same sort of gas content, and same sort of star formation rates. So again, properties are quite similar between the spherical one and the most extreme elliptical. However, true ellipticals are really only mildly elliptical, so from E0 to E3. And beyond that, they're not elliptical galaxies, we believe, anymore. So what are they? Well, when we do detailed spectroscopic measurements, that means we're looking at the light given off by them, and we essentially split the light out, a bit like a rainbow, and we can analyze that light. And by doing so, we can calculate the rotations of these. And when you get to the E4 to E7, these are actually rotating like a disc. So these have disc-like dynamics, whereas the true ellipticals don't. So when you get to like E3, it's slightly kind of squashed, but it doesn't have a significant net rotation like a disc. So from E4 to E7, they do have these disc-like dynamics. How do we do that? Well, here's an example with Webb and spectroscopy, really, if you're not familiar with it. You take the light from any astronomical object and you essentially split the light into the different wavelengths, and you can look for the intensity of light at those wavelengths. It helps you work out what the object is made from, but you can also use the Doppler effect. So the Doppler effect is where the wavelength is stretched or squeezed because it's moving away from us or towards us. So if we take a star, for example, a star that is travelling towards us is going to be blue shifted because the wavelength of light gets moved towards the blue part of the spectrum. It gets squashed, which means that it gets shorter, so it goes towards the blue part of the spectrum. When it moves away from us, it goes slightly redder. So we can use those lines in that spectrum of what it's actually made of, calculate how far they've actually shifted to get the velocity of that. So if you want to do that, or you want the actual equation for that, you can use it here for Doppler shift. So the velocity then is just going to equal the speed of light times the ratio of the shift in the wavelength and the stationary wavelength. So if the wavelength is stationary and isn't moving, then there's no velocity. But that delta lambda at the top there is how much that wavelength has shifted either in the blue or red direction. So they can work out the velocity. And what we do is we do that for the galaxy, across the galaxy, and we will find that one edge is going to be blue shifted, that's travelling towards us. One of those is going to be red shifted, that's moving away from us. And if we map that out, we end up working out that it's actually rotating like a disk. So that was what identified these E4 to E7 galaxies as being not elliptical galaxies. So what were they? Well, they're basically lenticulars. So these are lenticular galaxies that are hiding there kind of in plain sight as elliptical galaxies, but we still kind of use that in literature, and they might actually be noted as a S0 or an E something galaxy because they kind of are the same. So you might find that it might have, well, they have the wrong classifications basically because of them being edge on. When they're edge on, you really can't see the disk properly. They just look like a flattened elliptical galaxy.